This is R.D. Sharma solution, class 12, chapter 11, differentiation exercises 11.3. Differentiate tan inverse sin x by 1 plus cos x. The x limit is given as negative pi to pi. So that will be used if we do certain substitution. So this substitution, if you are not substituting, then this range you don't have to worry about. But in case you are substituting, then this range becomes very important, as I earlier reiterated. So this sin x, that is sin 2 theta, is 2 sin theta cos theta. So sin x is 2 sin x by 2 cos by x by 2, that you can write. So this we can always change. 1 plus cos x, which is the denominator, this can be changed to 2 cos square x by 2. 2 gets cancelled. 1 cos, 1 cos gets cancelled. So you just have sin x by 2 cos x by 2, that is tan x by 2. Now this is tan inverse of tan x by 2. So this tan and tan inverse gets cancelled. You have no substitution done. So y is basically x by 2. So you have to differentiate. You have to do dy by dx, which is equal to half. Differentiation of x is 1 only. So dy by dx is half here. This is your final solution. Differentiate sin inverse 1 by under root 1 plus x squared. So what we will do here is we want something inside as sine. So this 1 plus cot square theta is equal to cosec square theta, that we already know. But the question is, you will ask, why are you not using 1 plus tan square theta, that will be equal to sec square theta? Why are you not using it? Because we have a sine inverse outside. So we need a sine inside, so that this sine and sine inverse can be cancelled. Of course, we can apply anything, but we have to solve the question. So this is 1 by x, I am putting it as cot theta. So 1 plus cot square theta, that is under root of 1 plus cot square theta. And this is 1 by 1 plus cot square theta is what? Cosec square theta. Under root of cosec square theta is cosec theta. So finally cosec theta will come. So let me write it as cosec theta. And we already know 1 by sin theta is cosec theta is 1 by sin theta. So it becomes sin theta. What is outside? It is sin inverse. Now since there is no limits being given or the boundary being given, you can always cancel these two out. So that is only theta will remain. But what is theta? We took cot theta as x. So theta was cot inverse x. So this theta, you can replace it by cot inverse x. And now we have to differentiate this cot inverse x. What is the differentiation of cot inverse x? Dy by dx of this cot inverse x is minus 1 by 1 plus x square. That is your final answer. Differentiate cos inverse 1 minus x to the power 2n divided by 1 plus x to the power 2n. So what we have to do for the inside thing, we need to come up with certain solutions so that cos comes. This comes with certain cos thing. So 1 minus x to the power 2n, you can always write it as x to the power n to the power 2. This is 1 plus x to the power n to the power 2. Now this x to the power n, you can replace it by certain thing like tan theta. So you get tan square theta and tan square theta numerator denominator. What I am trying to say is 1 minus tan square theta divided by 1 plus tan square theta, that is. 1 minus tan square theta divided by 1 plus tan square theta is always cos 2 theta. That we know by trigonometric discussion we already had in the previous classes. So cos 2 theta is now, in terms of cos, we have a cos inverse outside. So it will be cos inverse cos of 2 theta. Now this you can cancel, you have a 2 theta. So how do we get theta here? Tan theta is x to the power n. Theta is tan inverse x to the power n. So 2 into 10 to the power inverse x to the power n. So why is this? And there is, but before that, as I already told you, you have to check for the limit. The x range is what? 0 to infinity. That is, x is between 0 to infinity. What you have to check? You have to check for 2 theta, because that 2 theta is finally coming when you cancel cos and cos inverse. and that can only be cancelled when you have 0 to pi in between. So x to the power n, you just take the power of 0 to the power n, and infinite to the power n, 0 to the power n is 0, infinite to the power n is infinite only. So 0, this is x to the power n, you can just write it as tan theta, and this is infinite. Now you can just take tan inverse on all the sides. So what do you get? Tan inverse 0 is 0, tan inverse of tan theta is theta, so 0. Here you get theta, and tan inverse of infinity is of course pi by 2. So you can just write pi by 2 here. Now you need 2 theta. So you have to multiply this all by 2. Twice of this. So 2 into 0 is 0. Here you have 2 theta. And then twice of pi by 2 is pi only. Now since it is between 0 and pi, and cos inverse cos theta is theta only if you have theta between 0 and pi, which is actually the case here. So we have checked and verified it. Now we can easily differentiate 2 tan inverse x to the power n, which we came up just a few seconds back. Because we are into the limits, we are not gone out of the bound. So this is 2 tan inverse x to the power n. So dy by dx will be equal to 2, and we have tan inverse x to the power n. Tan inverse is simply 1 by 1 plus that content square, so x to the power n is there, so it is square x to the power 2n. Now differentiation of x to the power n is also to be done, which is simply n x to the power n minus 1. This is the basic differentiation formula. So what do you get? N x to the power n minus 1. Denominator you have 1 plus x to the power 2n, twice of this. Okay. So 2n x to the power n minus 1 by 1 plus x to the power 2n is the final answer. This is your dy by dx. Okay. Differentiate sin inverse 1 minus x square by 1 plus x square plus sec inverse 1 plus x square by 1 minus x square. Now this kind of question seems complicated, but just by one trick, one thing, this becomes so easy, you will not comprehend. See, this sec inverse and cos inverse are reciprocal. Sin inverse, cosec inverse, reciprocal. Tan inverse, cot inverse, reciprocal. Alright? So this is sec inverse 1 plus x square by 1 minus x square. So when you have sec inverse x, you can always write it as cos inverse 1 by x, and that is other way around also. That is cos inverse x is sec inverse 1 by x. So this sec inverse x can be written as cos inverse 1 by x. So cos inverse x will be sec inverse 1 by x. No. So this sec inverse x can be written as the reciprocal of whatever is inside. So you have sin inverse 1 minus x square by 1 plus x square, that is always there. Call it as theta, sin inverse theta. Plus, when you take sec inverse and when you convert it into cos inverse, this 1 plus x square and 1 minus x square, the numerator denominator will change the position. Then it will be 1 minus x square by 1 plus x square. And sin inverse theta plus cos inverse theta is always pi by 2. That we already know. So what do we get? Y is simply pi by 2. So differentiation is dy by dx of pi by 2. Pi by 2 is a constant, it is going to be a 0. Differentiate tan inverse a plus x by 1 minus ax. So we have a, which is the one term, x as the other term. So we have the first term plus second term divided by 1 minus first term into second term. Now we know what kind of formula it will be. Because it is tan inverse outside, we need a tan inside, so that we can cancel it out. But here we have a direct formula. Tan inverse x plus tan inverse y is tan inverse x plus y by 1 minus xy. This we already know. So this is tan inverse. So this is a, say a and b. I'm just telling you the formula. If it is x plus y by 1 minus xy, that is simply equal to tan inverse x plus tan inverse y. Alright? So this is tan inverse x plus tan inverse y. Alright? So tan inverse x plus y by 1 minus xy is this. So tan is actually coming in picture, which we want. We want tan to come in picture. So this one is a and x. So it will be tan inverse a plus tan inverse x by the analogy of the formula which we just discussed. So tan inverse a plus x by 1 minus ax is tan inverse a plus tan inverse x. There are two terms a and x, which is fulfilling the criteria of this kind of trigonometric identity or equality. So tan inverse a plus tan inverse x, you just have to differentiate it. Why is this? When you differentiate d by dx of tan inverse a is a constant, it will be a 0 only. You have to have a x to differentiate with respect to x, of course. Now tan inverse x, differentiation of this is 1 by 1 plus x square. So y is equal to 1 by 1 plus x square. This is your final answer. So because we have not changed anything, no substitution, no limits, no boundaries, so it's the final answer. Same thing here, tan inverse under root x plus under root a divided by 1 minus this under root x into a can be written as under root x into under root a. This can be written as under root x into under root a. So this is your p, assume it to be p plus q by 1 minus p into q, and that is equal to tan inverse p plus tan inverse q, which we have just seen in the previous question. And the p and q is under root x and under root a. So it will be tan inverse under root x plus tan inverse under root a. Alright? So dy by dx it is going on. So d by dx of tan inverse under root x plus dy by dx of tan inverse under root a. Since this dy by dx of under root a is going to be 0, whatever tan inverse it is, we just have to worry about dy by dx of tan inverse under root x. That is the final answer. And this is by 1 plus under root x whole square. Under root x square is x only. So you have 1 by 1 plus x. And dy by dx of under root x also we have to do. And root x differentiation is what? 1 by twice of under root x. So we just write 1 by twice of under root x. So we have 1 by twice of under root x, and inside this we have 1 plus x. Okay. So this solution I have provided just to know that this is how you are going to write. I always tell the logic and reasoning of the answer, how you are going to solve, but in examination you have to write it like this. Now this tan inverse a plus b tan x, b minus a tan x. So most of the questions which are coming just after this is all about converting certain thing so that you get a tan inside. Because tan inverse is also outside, you need somehow tan inside. Okay. So this a plus b, I am taking the inside one, a plus b tan x divided by b minus a tan x. So how to resolve this? We can divide the numerator denominator by b. A by b, b by b, b by b, a by b. Now this a by b, let it be like this, a by b. And this b by b gets cancelled, this also b by b cancelled. So this is 1 and 1. So finally a by b plus tan x, 1 minus a by b into tan x. Okay. So tan inverse, this will get cancelled. So the inside one, which is this, we have to come up with some tan sort. So we have tan inverse a by b. I am writing a by b as tan inverse a by b because tan and tan inverse gets cancelled. So a by b can be written as tan inverse a by b. This is very important to understand. Again in the denominator, a by b, in place of a by b I am writing it as tan into tan inverse a by b. Tan x is already there. So eventually this tan inverse a by b is a by b only. We have changed this because this first term plus second term divided by 1 minus first term into second term, that is p plus q divided by 1 minus p into q, is nothing but tan of p plus q. What is p here? Tan of this tan inverse a by b is p, that is the theta inside. And the second theta is x. I hope you got the idea. It will be tan inverse a by b, because the first theta is tan inverse a by b, the second theta is x. Whatever is inside tan inverse is your theta, of course. So it will be tan inverse a by b plus x. So this content is the first angle, the second angle is x. So this will be tan inverse a by b plus x. So you already have a tan inverse outside, cancel this out. So what it is remaining, tan inverse a by b plus x. Now you can just differentiate it, dy by dx. Tan inverse a by b is what? 1 by. See, tan inverse A by B is, you don't have to worry about this because this is a constant. Constant differentiation is 0. So don't worry about that. It will be 0. Only differentiation of x is going to be 1. So dy by dx is 1 only. Differentiate tan inverse A plus bx by b minus ax. So I hope if you understood the previous question, this is a piece of cake for you, because a plus bx divided by b minus ax, which is inside, we need to divide it by b. This also b, this is b, this is b, and this is b. So this is a by b plus bb gets cancelled. You have x here. The b by b is 1 minus is there. And then we have a by b x. Same thing here. This, see, tan inverse is already outside. And this is corresponding to tan inverse x plus tan inverse y. What is x? A by b. What is y? Which is x. If I just take some random p and q, this p plus q by 1 minus p into q is tan inverse p plus tan inverse q. Okay, you got the idea? So tan inverse a by b, it will be tan inverse a by b plus tan inverse x. That is your final result in this case. Okay. So this tan inverse a by b plus tan inverse x is y, dy dx of y. This becomes 0. Tan inverse a y will be 0. And tan inverse x differentiation is of course 1 by 1 plus x square. This is dy by dx. Alright. This is your final answer. Differentiate tan inverse x minus a by x plus a. Okay. So for this, again, divide it by x so that you get a relation in terms of tan, because tan inverse is already outside. So let us divide the numerator denominator by x. So what do you get? 1 minus a by x divided by 1 plus a by x. So we assume that it is 1 into a by x. The first one is 1. The second one is a by x. When you have tan inverse outside this, what does it mean? It is simply tan inverse of first term, which is 1, minus tan inverse of a by x. Remember, it is negative in the numerator, denominator it is positive. So now it will be tan inverse 1 minus tan inverse a by x. Now this is y. Now let us differentiate it d by dx of this. So this is a constant, tan inverse of 1 is constant, it will be 0. And tan inverse a by x, it is simply 1 by 1 plus a by x whole square. And then differentiation of a by x, d by dx of a by x. So this is going to be 1 by 1 plus a by x whole square, which is x square plus a square by x square goes up. Differentiation of a by x, a will be constant, so it can come out. 1 by x is minus 1 by x square. Okay. So finally it will be, this denominator will be, see, 1 plus a square by x square is x square plus a square, this x square goes up. So it will be, finally this result will be x square by a square plus x square, or x square plus x square, a square. A is already there. And since we have negative, there is a negative sign also, because tan inverse 1 was 0, remember? So we have a negative from differentiation of a by x. We have a negative outside also. So negative becomes positive. This is negative and this negative. So it becomes positive. So you have this a by x square plus a square. That is going to be your final answer. Okay. Differentiate tan inverse x by 1 plus 6x square. You need tan inside, or whatever formation you can make so that you get a tan inverse relation. 6x square is 6 into x square, can be written as 6 into x into x. 6 can be written as 2 into 3, x into x. So this is 3x into 2x. 3x into 2x is 6x square. Okay, what is the use? Because the numerator is x, and x can be written as 3x minus 2x, and that is going to be x. So in place of x, I am replacing it by 3x minus 2x. The denominator, it is going to be 1 plus, it is not negative plus, okay, I'll just change it. 3x into 2x, 3x into 2x is 6x square. So you have a tan inverse outside, and you know by up till now what we have done. It will be tan inverse 3x minus tan inverse 2x, because tan inverse x minus tan inverse y is tan inverse x minus y by 1 plus xy. Right? So this is the relation. You have to remember it. So tan inverse 3x minus tan inverse 2x, we have to differentiate. This is your final thing. Let's differentiate it. So why is this? d by dx of these two. So tan inverse 3x is 1 by 1 plus 3x whole square. And differentiation of 3x is 3 only. d by dx of 3x minus d by dx of. So we have 1 plus 2x whole square. And d by dx of 2x. 2x it is. So this 1 by 1 plus 3 is a 9. 9x square it will be. And d by dx of 3x will give you 3 only. So 3 in the numerator. Minus d by dx of 2x is x only, 2 only, and 1 by 2x whole square is 4x square. This is your final answer. If you solve it, that will not be a very good idea, because you are not going to gain anything. This is your final answer. Alright.